Super. Okay. Great. So, hi everyone. Welcome to my first lecture. This is very exciting. I am going to be talking today about relational database design, as this slide shows. And what I'd like to do for this session is spend about the first maybe half an hour, 45 minutes, or up to 45 minutes, talking about databases, how to design them, and then kind of live designing a schema for a subset of features from the Quora application, the question answer application. And then I'll save the last 15 minutes at least for questions. So what I'd love for you to do is if you have things as I'm talking about that like are really confusing to you and like you just need a clarification really quickly, please interrupt me. I might not be able to see and notice if you send me a chat in Zoom chat, but I have my Slack open on my monitor, so feel free to like send a message in Slack or just unmute yourself and literally interrupt me with your voice. I don't mind at all, and then we can move on from there. If, however, you have a question that is kind of more broad, or you want to know kind of go on a different track, please just write your question down in some notes somewhere and save it for the end of the lecture, and we can kind of dig a bit deeper. For example, if you have a question about transactions and what transactions are and how we can use them, that's something that I'm not going to explain midway through this lecture, but I'd be happy to talk about at the end. Okay, great. So, relational database design. The first thing that I'll talk about is introduce just some key terms. There's some vocabulary here that you might be familiar with, and I want to go over some of them and clarify what I mean, and leave them kind of around so that if you hear me use these terms again, you'll know what I'm referring to, and you can always go back to this slide if you want to and reference them. So the main key terms that we want to think about when we're thinking about designing relational databases are tables. So tables and relations can be used interchangeably. I use this slash here to say that these two terms are usually used interchangeably. They're basically synonyms for all intents and purposes. Columns or fields, rows or records, the different kinds of relationships between tables. So a one-to-one relationship, a one-to-many, or a many-to-many relationship. The different data types that fields can have within a table or relation. So varchar for storing a short string of characters, date for storing date objects, date strings, numeric for storing numeric types, etc. And then the schema, when we say schema, usually what we're referring to is either the overall kind of grouping of all relations within a database, or sometimes you'll say like just the table schema. And so we're talking about just a table schema, we're talking about the names of the fields, their data types for a particular table. When I say schema, what I'm not talking about is the actual data stored in a database. So before I move on to the next slide, I just want to introduce the kind of like the common metaphor for databases, or not metaphor, but the common example that people usually use to give you a visual sense of how this works is a spreadsheet, right? If you've worked with Excel or Google Sheets, you're familiar with the concept of rows and columns. And even within a sheet, you can have within like one spreadsheet, you can have multiple tabs that each have their own kind of subsheet. So to map these concepts to a spreadsheet application like Excel, you could think of tables as those tabs. So each tab kind of having its own grid of rows and columns. The columns being columns, the rows being rows. The data types, or the column titles, the field names, those would be the first. So in a spreadsheet, you have a header row, where usually it's like the first row and it's in bold, and you say things like the name of the kind of data it's storing, so ID or birthday or date or something like that. And so when we're talking about the schema, usually what I'm talking about, the equivalent there is saying sort of what are all the different column names of a spreadsheet and the different table names within that spreadsheet. Actually, the different tab names in the spreadsheet. That's kind of a rough example if you just want to have some kind of visual. And if you work with a SQL visualization tool like Postico, for example, you'll see some very familiar graphics that should remind you of like an Excel style user interface. Awesome. So a few more terms, slightly more advanced, that I tried to split up into 2 slides, where the first one is, oh man, this is really slow. The first one is more kind of explicit terms that you'll see all over the place. These ones are things that you are kind of slightly more advanced terms in document databases. So the first one is queries. So a query is literally just a message sent to a database somewhere. And so you've probably seen queries like select, insert, update, or delete. These are different kinds of things, kinds of messages you can send to a database within SQL, within the SQL language. For keys, primary or foreign keys. Primary keys meaning a way to indicate the identity of a particular row or record. And a foreign key is meant to say that this is an ID that refers to a record on some other table. So kind of primary referring to my own table, within my own table, foreign referring to some other table. Constraints, so different kinds of constraints that you can have on a database or a database table. So uniqueness constraint you can apply to fields, to columns, to say that you should only ever have you should never have a duplicate value within that field. So for example, if you have a column email in the users table, you might enforce uniqueness constraints. They don't have the same email twice, since emails should be unique. And not null is, all the not null says is always make sure that this field has a value in it. So in other words, there's no empty fields in your React database. And a few of the things that you'll hear, join tables, you've encountered those. We'll get to those later on as well. Normalization and denormalization. This refers to the process of kind of a series of processes for making a database either more kind of better structured and reducing duplication to reduce the possibility of errors. That's normalization, it's kind of reducing duplication and making sure that there's less room for errors to occur, all different categories of errors. And denormalization is a process of actually intentionally duplicating data to make what's called read operations, in other words, reading data from the database more efficient. And then indexes are another word you'll hear when the primary purpose of an index is to make it very efficient to do read operations when searching by a particular field. So you might, for example, back to the users table example, you might have an index on an email, which would say, essentially makes it very easy and efficient to search for a user by that given email. If you're doing lots of operations where you're saying, find me a user with this email, adding an index to that field will speed up the operations there. But as I said, these are all kind of more advanced things we'll get to in a sec. So we have these terms. Feel free to refer back to these slides in the spreadsheet or in the presentation. Finally, what is SQL? Man, Chrome is just taking forever. Let me close some of these tabs. Okay, so SQL stands for Structured Query Language. It was invented by IBM back in the late 70s, I believe, early 70s. And the premise for SQL was to give kind of the lay customers, non-technical customers, the ability to interact with a database without having to know a lot of advanced programming techniques, without having to know any programming at all, actually. And it's very tightly coupled to the concept of relational database. So let me just back up a sec and define relational databases in contrast to other kinds of databases. So when we're talking about relational databases, what we're really talking about is a database that organizes data in the form of tables with columns and rows. Or in other words, tables, relations with fields and records, another kind of language to use. And that everything gets represented in this kind of abstract concept. And the relational part of that relational database is that you can use tables to connect and create relationships between different records across different tables. It's the kind of like one-to-one, one-to-many, many-to-many relationship. That's the whole kind of idea behind relational data. And in contrast to a non-relational database. Maybe the most simple example of a non-relational database is something like a key value store. So you might have heard of this technology called Redis as an example of a very popular key value store. And a key value store is just a database that allows you to retrieve values for a certain key, just like an object in JavaScript. Or it's often called like a hash table lookup in other languages. And that's about kind of the simplest concept of database you could get. It's like you just have these values and there's no relationship between them. It's just everything has its own key and its own value. And there's not connections. You may have heard of databases like Mongo, or what are some of the good examples of non-SQL databases. There's a graph databases like Neo4j. These all use different kind of concepts of storing and manipulating and querying data, that don't follow this kind of strict tabular model. So back to this slide. What is SQL? So a little bit of history. Invented by IBM in the 70s to basically provide an interface for kind of your regular business customers to do things like extract data, interact with the database without having to know whatever language the database is implemented in. And so this is why the language of SQL is fairly syntax light. You'll notice like it doesn't have a lot of sort of structure to it in the sense of like how JavaScript has lots of curly braces and syntax of defining variables and things like that. SQL has gotten very advanced, so you wouldn't really call it a programming language, but it is a query language, and it is quite a complicated language. But its initial intent was to read kind of more fluidly than the language of the time. And then, so SQL itself is it's a standard that a lot of different database software implements. So these different variations of databases like MySQL, Postgres, both of these are open source. Oracle, SQL Server, SQLite, these are all different kinds of database that all implement the SQL standard, but they have their own additions to it. So the analogy I like to use here is that SQL is kind of like a lingua franca, like Swahili, for example, where different databases kind of like have the same basic language, all the key structure is there, but different. But they have these different variations and dialects in between them. So just like Swahili is kind of one big language where somebody who speaks Swahili from one part of the world can understand somebody else fairly well. There's still a lot of things that will be different in regional dialects and differences. And so the same thing, like when you're writing SQL for Postgres and you wanted to say, run the same SQL on a MySQL database, depends on the complexity of the query, but some of it might run and some of it might not. There might be some kind of quirks and inconsistencies you're not used to. And so you have to make sure that whatever database you're using, you're familiar, or in other words, you're sure that you're using the kind of correct variation of SQL for that database. And SQLite, if you haven't encountered it yet, is an interesting place to start. It's a very small database. It actually runs as a file, and it implements a subset of the SQL standard. So you don't have kind of like the full scope of things. Whereas Postgres, for example, is a very complex and big database that has a lot of stuff going on that you can do. Anyway, so SQL is the language we use to interact with the database. And those are kind of the key foundations I wanted to sort of establish before we get going. And now let's jump into the case study. So I'd like to spend the next 15 minutes to half an hour working on database design for an application that already exists, just to give us some shared context. But you can imagine that database design would usually take place at the kind of the stage of product development after you already know kind of what the basic features are you're aiming to get. But you don't yet know how you want to structure or store the data. Some people, there's like a bit of a debate on sort of like whether database design should come first or whether you should do like build your UI first. I'm generally of the camp that believes that you should kind of focus on building your UI first and focus on what it is that the user actually needs and wants, and then figure out how to model your data to meet those needs after the fact. So for the sake of this case study, we're going to follow that pattern. and assume that there's already some feature set or user stories that we have that has been designed by a UX designer or product designer or whatever. And we're just going to take those and figure out how can we build a database to satisfy this application. So steps in the design process. Starting with user stories, what we'll do is then translate these into questions, identify the nouns and the kind of the things within the questions that we're working with, and from that, make a schema. Then we'll normalize the schema, kind of pare it down and make sure that it's efficient and well-designed. And then we'll test this design against our initial questions and stories and make sure that the design satisfies those questions and stories effectively. So let's start with these stories. So for Quora, what I did is I just looked at the application and I kind of came up with a set of these user stories that at some point the designers of Quora probably had something similar to this. This is obviously a subset of everything that Quora can do. There's a lot more advanced features, but I'm going to try and focus on just the core features in this application. So within Quora, users can post questions. They can post answers for questions. Questions can be answered more than once. You can upvote and downvote answers. Questions can be grouped into different topics, for example, programming or databases. Users can follow questions, meaning you get updates, notifications on them when their new answers come out. Users can see how recently a question has been followed, so you can see kind of if a question has been followed in the last day or so. And as a user, you can see all of your posted questions and answers, all the things that you've posted. So these are sort of a rough set of user stories that might have been handed to a UI designer. In this case, they're handed to us, database designers. What I'm going to do is translate these stories into a series of questions. And the reason that I do this is because a query, most of the queries that you think about are going to be queries of reading data. So you're basically asking a question of the database. The database needs to figure out how to answer that question and provide you with the data you're searching for. The kind of analogy of a question doesn't really hold up to operations besides select, besides read operations. But in most cases, if you are writing or updating data to the database, in other words, using an insert, a update, or delete statement, chances are that data that you're writing, you'll also be reading out somewhere else as well. So everything that you read is going to contain basically everything you will ever write or delete usually as well. So questions are a good place to start because they kind of cover the full surface area of the things you need to be able to store and extract from your database. So I took those stories and basically said these questions that a user, that an application is kind of implicitly asking when you're using Quora are things like, what are the questions in topic X? As a user, this is kind of like a question I'm asking. If I'm visiting the page for topic X, and X in this case could be like whatever, JavaScript as a topic, then my interest is in finding the questions about that topic. And so I want the database to provide those back to me. What are the answers for question X? After I've seen a question, I want to see a list of answers. Which answer has been upvoted the most? When was question X posted? How many followers does question X have? When was question X last followed? And then I can do things like, what are all the questions that answered posted by user X? So given a user, what questions have been posted? And these questions are going to be kind of my seed for the initial queries. And you could see how, for example, if I wanted to write a query to see what are all the questions in topic X, like it's not too many steps to follow to say, well, I could say something like select star from questions, if I had a table named questions, where topic ID or topic is equal to whatever X is, in this case, in JavaScript. So these questions can then be kind of translated into example queries that we can then use as sort of our initial test suite, so to speak, even though we're not actually writing a test suite for this. But there's a way to drive design. This is kind of a nice start. And what I'll do next is take these questions and identify all of the nouns within them. So from the questions above, I want to look at the different nouns that are in here. So let me go back to it. It's like question, topic, answer, question, answer, upvote is a verb, but there might be a noun kind of hidden in there. The question. There's posted is also a verb. I don't think it really qualifies as its own noun. There's no kind of notion of the post in here. So questions, answers, and users seem to be the most commonly used nouns here. And what I want to do next is sort of figure out, are these nouns sort of things in and of themselves, or are they properties of a thing? So for example, a name is also a noun, but a name is really just more of a property for a user. And the reason I do this is because if they are sort of things that own themselves, that are of themselves, they usually can be translated into a table in a database design. Whereas if they are properties of the thing, that means they're probably a column or a field in that table. So of all the things that I can think of beneath these three nouns, questions have the most. So this is a question-based application. So they have things like the question text, the number of upvotes or downvotes, the topics for this question, the posted date time, the followers for this question, the last follow date time. Answers have things like their text, the answer and user, the posted date time. Users have things like a name, their job title. I'll add that name, job title. And a profile picture. And you'll notice when I'm doing this, I'm actually not, I'm not thinking so far ahead to the sort of sub-tables or join tables that might be in the database. For example, like upvotes and downvotes. This is probably going to end up being a table in and of itself. In other words, like a votes table. You have like up and down votes because we probably want to associate these upvotes and downvotes with actual users. But for the sake of just my design, I'm just organizing it under questions because they kind of like, their whole purpose is to support a question. And so they're kind of like, for the sake of our initial design, they're just for properties of question. And I can go through and extract them out and make them their own thing later. That's sort of the process of denormalization. So let's get into it. I want to do some actual schema design for this question application. So what I'm going to do is pull up Atom. And I've got nothing. Let me create a new file. So I'm just going to write some SQL here. And I'll do this on the right side of my screen. And I'm going to pull up my questions for the left side of the screen. All right, so first thing to think about is what are our tables? So probably have a table questions, a table answers, and a table users. So let's go ahead and create some of these tables. Create table questions. And I'm going to leave this blank for now. Create, well, actually, every table, so kind of just by standard, every table is going to have an ID. It's going to be of type serial. And never going to be null. Actually, I think serial is implied that it's not null, but I'll just add that as an explicit constraint anyway. So I'll do this 3 times just to start us off with a good baseline. And users. Okay. And then what else did I say? So questions and answers. What are the answers for question X? So already the second question here, I'm sorry, answer the first question. What are the questions in topic X? So let's say that questions have a topic. The topic is probably going to be some small string like whatever, calculus or JavaScript or I don't know, history. So we'll make this a variable character, and I think every question in Quora has to have a topic, so I'm going to make this not null as well. And that would answer the first question here. What are the questions within topic X? So I can sort of search and filter by a topic. The next one is, what are the answers for question X? So here's my first example of a relationship, because I now need to connect some question X with an answer. And the relationships, or whether it's a one-to-one, a one-to-many, or a many-to-many, is actually kind of baked into this question right here. I know that basically that one question will have many answers, because the question asks, what are the answers for a single question? And there's nowhere that I think I would need to say, does an answer apply to multiple questions? I'm pretty sure that the intent of the application is to say that there's one question with multiple different kinds of answers, but that answer won't be answering multiple questions. So in other words, it is a one-to-many. And the way that this one-to-many works is it's one question for many answers. Because that's the case, I know that in order to make this, or design my schema to support that one-to-many relationship, I need to reference the question from the answer. So the answer needs to carry around whatever question it belongs to. And to do that, I'll create a reference, a foreign key, basically. I'm not going to add the foreign key constraint yet, but for the sake of just designing the schema, I'm going to add a foreign key called question ID, and this is an integer, and it will be not null, because every answer should belong to a question. You don't want to answer a non-existent question. I think I can also just say foreign key. Can I do that? Yeah, I can do that here too. I'm pretty sure. So all I'm saying is that this question ID references table questions. Actually, I'm going to double check my PostgreSQL. I can't remember if it's foreign key or if it's references and then references questions.id. I think that might be the correct syntax. I'll come back to it. Okay, so what I'm saying here is that it references the ID field of the questions table. And that should allow me to answer question 2. The next one is, which answer has been upvoted the most for question X? So here, I think we could probably just say, this is like upvotes. And this will just be an integer. We don't need to make this a decimal number because you can't half upvote something. You can only upvote it or downvote it. So this will just be an upvote, and we'll say default is 0 here. So it starts off with 0 upvotes. Should also not be null. All right, when was question X posted? Okay, to answer that question, questions should probably have a created at or some kind of timestamp to tell me when it was posted. So we could call it posted at, and this is a date time, and this is not null. How many followers does question X have? Okay, so followers here, all the question seems to be asking is for a count of something. So I'm just going to say that followers is an integer, and default 0 and not null. This is an area where I'm kind of like, I'm guessing this is going to be pulled out in the process of normalization into its own join table or something, because a follower really represents a user following a question. But for now, I'm just going to do the most simple design possible. So followers is an integer. When was question X last followed? So to answer this, again, I'll kind of go with like the simple answer. This would be like last followed at date time. And this can be null, because if there are 0 followers, then there is no last followed at time. And what are all the questions and answers posted by user X? Okay, so in the users table, we're basically saying that a user posts questions and answers. So again, this is showing me a relationship between these two tables. And I need to ask, is it one-to-one? Is there always one question for one user? No, that's not quite true. Users can post multiple questions. So it seems like it's a one-to-many. And the next thing is it a many-to-many? Can one question be posted by multiple users? And the answer is no. You only have one user posting multiple questions. Same thing for answers. You wouldn't have two users posting the same answer. So in this case, it's two one-to-many relationships where there's one user for many questions and one user for many answers, which means I need two foreign keys, one in questions and one in answers for the user ID. And in this case, the convention for writing foreign keys like this is to use the table name, but in singular form rather than plural form. And then reference it, make it the integer the same data type as the ID. References users.id. The same thing down here to kind of group my foreign keys here. Okay, question ID and user ID. So again, this is the convention to use the singular form of the table name plus underscore ID. However, I think this convention can be broken when the relationship can be better expressed more clearly. So for example, like by just putting user ID in questions, it's not super clear what the relationship is between the user and the question. Did they create the question? Did they ask the question? Did they upvote the question? Are they an admin who allowed the question to happen? And so what I want to do is make it explicitly clear that this is a user that created this question. They posted this question. So I might just follow the same language used above of posted at and say like posted by ID. So this is perfectly valid because I'm saying right here which table it's referencing, but it's a bit more clear in what the relationship is. It's not saying, well, this is posted by a user with ID X. And same thing, answers, I think I'll use the same convention with posted by here to show that users post questions and answers. Okay, so that schema roughly satisfies the questions that we have right here, but it's not super well normalized. It doesn't have it has some duplication in here, and it's not expressive of all the relationships that are in here. For example, we're going to have some duplicate data, and one of the reasons I know this is because let's say there are 20 questions with the topic of JavaScript. That means that the string JavaScript is going to appear 20 times in records in the questions table. So this topic is going to get duplicated over and over again. So that's an area of duplication. I just realized though that the schema doesn't even meet our original constraints. I need to go back real quickly. So put pause on the normalization. I need to fill out the rest of the fields that actually need to satisfy the key data. So right now the question is missing text. We need to have question text. And this will be a text field because it could be pretty long. And this will be not null. You can't have a question without the text. Maybe question text is the wrong words since this is, we don't have text and text be like the text type and the field name be text as well. I'll call this, let's see, let's call it, what is a good name for this? I'm inclined to go question text, but that's a bit redundant because now I would do things like questions, question text, which is like, well, if it's the text of a question, then I don't need to repeat myself twice. So I'm going to just say, I'll say it's text for now and ignore the syntax highlighting. It shouldn't be too much of a problem. But if it gives me errors later, then I'll know where to go to fix that. Okay, and answers, I think I'll have the same thing. There's an answer text, and it's going to be text and not null. And then users should have something like, what did I say? They have a job title, so job title, and varchar, this can be null, and a name, this is varchar, and not null, we should have a name. and a profile pic. So profile pic is actually going to be, I should say profile pic URL. This should be a URL towards their whatever image. This is also going to be a varchar. Okay, then I also want to have a posted at time for answers to keep track of when this was, when the answer was posted. Okay, so this schema roughly satisfies the kind of basic cases. Let's get into normalization. So what am I doing in normalization? When I'm normalizing the database, this is kind of a large field of work and encompasses a lot of different things. But for the sake of this exercise, what I want to focus on is check for missing relationships, identify those relationships, create any join tables, and get rid of duplicate data. So those are kind of the things that I want to focus my time on in refining the schema that I have right now and making sure that it's a well-normalized database schema. So I mentioned earlier that one of the places for duplication is this concept of a topic. So if we had many questions with the same topic, we're duplicating that same string over and over again. And it would be a bit more optimal in terms of saving space to have topics be their own table, so that there is a topics table, and then questions can reference that topic table. So every question would have a topic ID if they belong to one topic, and that would be its own table. So I'll just go ahead and do that now and say that we're going to have a create table topics. And it's going to have an ID like everything else, and a topic name. It's going to be varchar not null. And that's it for the topics table. And then questions now, instead of having a topic field, it'll have a topic ID as an integer, not null, and references topics.id. So that gets rid of the duplication of data inside of the questions table. So now I know that every question belongs to a topic. It's a one-to-many relationship. The topic has many questions. All right, what else do we have? Okay, so next thing we have is this concept of followers. And right now my schema is just assuming that followers is just a number that's being tracked somewhere. So a question just has a number of followers, and every time we increment this number, we would maybe store the data that was incremented. But what's kind of missing, there's like an implied relationship here that I imagine our application designers expect us to fulfill, which is that a follower is not just a number, it's actually a user. There's a person behind that number. And when somebody follows a question, we're going to need to do things like send notifications to that user. So we need to know who this follower is. There's like more data there. And so what this is hinting at to me is that there's some relationship between questions and users. So followers is actually a missing relationship between questions and users. And I need to figure out what kind of relationship that is. So if a user is following a question, then I guess the assumption is that users can follow many questions. And the inverse is also true. A question can have many followers. There's not just one follower per question. A user is not just following one question at a time. So this looks like a many-to-many relationship, many questions to many users, which means that we have a join table needed. And this join table actually has a name. We can call it followers because that is really the relationship that we're expressing here, is the following relationship. So create table followers. And within this table, it's just going to do, let's see, a few things. It'll have an ID because every table should have an ID. But we need to connect both the questions table and the users table. So we'll need a question ID and the user ID. So user ID, integer, not null, not integer. References users.id. And this way, I can get rid of this followers count in questions. And now if I have followers, there's this question that they're following and the user for the follower, I can actually change this called the follower ID to be more explicit that this is the person following the question. So that takes care of the count, because now we can just run a query where we say, select all of the followers for a question with X ID, and that would give us a count of all the followers. Takes care of our previous field here. And then the next thing to know is that the last time it was followed. So I think the easiest thing to do here is let's add a datetime. We'll call this followed at, and this is a datetime. And this should be not null. I'll make sure that we're always keeping track of when somebody follows a question. And that way we can just, to get the last followed at datetime, we'd find all of the followers for a question, sort them by datetime, descending, and then pick the first one off that list. So that that's the last one. All right, that takes care of that extra field. And the final thing to normalize here is this concept of votes. So this is actually a bit of a, this might be over-designing at this point. Like, I'm gonna go a bit further than we really need to for the sake of the sort of specs as they come into us, which is that votes are just a number. So you could think of an application that has like answers can be upvoted or downvoted. And so the number would increment or decrement over time. But there's, I believe in Quora, there is an association between a vote and a user. So in other words, like a user can't vote more than once, upvote or downvote more than once for any given answer, which I think is a good thing. You don't want somebody just like upvoting a question over and over again. So to enforce that constraint, we really need to know who this vote belongs to, which means that there is a relationship between answers and users that is the voting relationship. So an answer should have votes, and votes should come from a user, kind of like voter integrity. So this is another join table, I believe. One user can vote on many answers, and an answer can have votes from many users. So this is another join table, and we'll call this join table votes. So create table votes. And I'm just going to copy these over to get some templates in here. And this is going to be answer ID. And this is going to be voter ID. And then the final thing I need to know is whether this is an upvote or a downvote. So maybe I'll just have a vote value. And this would be either a positive or a negative integer. Default 1. So I'll say that the value by default is going to be positive, but they could also vote negatively. And that would take care of that upvoting piece. Okay, so the final thing, I know we're getting close to 15 minutes, so I want to just do one more thing before we wrap up, and that's do a design check. So this final piece of doing a design check, I want to check the schema against the initial questions and say things like, can all the questions be answered? In other words, of all the questions I want to ask of this database, is it complete? Can I actually get the data that I want? Non-redundancy, there are no duplications of data. I want to make sure I'm not duplicating data in multiple fields or tables. And then simplicity, is there only enough data to get the job done and no more? Like, did I add extra stuff that I actually don't really need? So let's start with completeness, and I'll go back to these questions. What are the questions in topic X? Can I do this? Well, I can find topic X, so the topic is JavaScript. I find topic with name JavaScript, get its ID, and then go to the questions with that topic ID. That question is answerable. What are the answers for question X? So given a question, I should be able to find all of the answers that have the question ID. There's this question ID field that references it. I can answer that question. And if I go through the rest of these questions, I believe I should be able to answer all of them. I'm not going to do that here for the sake of saving some time. But the last thing is there are some extra data here. I noticed that the questions don't actually ask anything about a user's job title. So I'm going to take this out and the profile pic. Both of these that seem kind of superfluous for the sake of this exercise. So we get rid of any data that actually isn't needed at all. And now we just have a nice, clean, simple schema. All right. That was 45 minutes of database design. I'm a little surprised we got to it at all. That was a lot. Let's take the last 15 minutes here and go over any questions you have. So I'll just do this in an ad hoc way. If it gets to be too complicated and people are asking questions at the same time, we'll make a queue. But what questions do you have? Feel free to unmute yourself and just ask them with your voice.
Hey, Tanner. I have a quick question.
Yeah.
So are you sure it's references and not foreign key? Because you said you'd come back to that.
Oh, I am not sure. I'd have to look up the Postgres foreign key syntax. Yeah, and I'm constantly referencing documentation for SQL schema or for SQL schema just because you want to know kind of what exactly you're working with here. So let's see, what about references? Oh, here we go. So it looks like, yeah, I can use references. I got to put the syntax is actually references, the table name, and then in parentheses, the field name. So references, yeah, if I do this, it should be like that, as opposed to the table name and the field name inside there. Yeah, okay, cool. Thanks, Zubir.
Cool. Yeah, thank you.
What other questions do y'all have?
Yeah, I'm a little bit confused about the references thing. I was wondering, does it actually change something in the database itself, or is it just for our own knowledge?
Yeah, good question. So I believe that references is actually, to some extent, it's not necessary. Like, let's say I had this answers table without the references in it at all. If I were to write a query like select, I want to get all the answers for a particular user, for example, select star from answers where answers dot user or posted by ID. By ID is equal to whatever my user ID is, say it's 4. Then basically there's no, the database doesn't need to know that this value is a user's ID. All I need to know that it's some number that appears in this field. So this would actually work, even if we didn't have references here, if this was commented out. We could still do this because this is a valid query. And I'm assuming 4 is coming from somewhere else in the application, probably not hard coding that value. What references and foreign key do is they add extra constraints to your database. And depending on the database implementation, they might allow things like faster lookups or the ability to ensure that you don't delete a record and then abandon its references. So for example, this is kind of a common case. Let's say that we have a bunch of answers, right, posted by you, and you have an ID of 27 in your users table. And then you decide to cancel your account with Quora. So you delete, the simple answer is like, okay, cancel the account, just delete the user record. But what happens to all of those answers that have your posted by ID at 27 now? Do they stay in the table? And if so, when somebody goes, hey, who answered this question, we're going to get an error, right? Because there's no longer a user with the ID of 27 in it. And so things like adding a foreign key constraint, what they usually do is we'll say, if you try and delete a value, delete a record, and their ID is referenced with a foreign key in some other table, the database will prevent you from doing that. It'll say, hey, I'm sorry, you can't delete this person, or you can't delete this record without also removing all of their references first. So it does things like that. References and foreign key are both constraints you can add on top of this field. But what's important for just making the connection work is purely that you have the same value, because it's just a simple where clause that compares these two values together. Does that make sense?
Yeah, it does. Thank you.
Yeah, no worries. Okay, any other questions?
Tanner?
Yeah.
you don't have to answer this today, but when I was, and I don't know if maybe the later modules have more information on this, but the SQL section online didn't have a lot on how to incorporate it into that app, like, and a lot of resources on that, and it'd be great to like see that part of things happen, and like maybe best practices on like database start scripts, and things like that.
Yeah, absolutely. Yeah, so I'll reference let's see, there was an example application that I built for integration testing. Example app was the address book app. I think this was it. If you're curious to see like sort of some basic examples of how to interface with a database from SQL, this is a decent one. It's fairly small. In here, there's just like a schema file and some queries. This is using the Postgres promise library. The reason I didn't get into it here is because these two things are basically orthogonal. Like you have databases, and then there's a whole other world, which is how to talk to database from any different language. So in JavaScript, for example, or in Node, there's probably several dozen, if not hundreds, of different libraries and tools for talking to a Postgres database. And then you also have all the other kinds of databases and other kinds of languages. So for any given database, there's probably going to be, kind of usually a few very accepted and popular, what's called drivers, drivers for a different language. But it totally varies on kind of how that driver implements things. So in Ruby, for example, you can talk to SQL databases with a library called Active Record. It's a pretty popular one. But each language will have their own driver for a database, and to learn about the particular driver, you need to go to that driver specifics documentation and resources. There's not kind of like one universal way to talk to SQL from JavaScript. It's all very based on implementation of the driver.
Cool, thank you. This is super helpful.
Yeah, no worries.
Hey, Tanner, I had a question. When is the best practice to use serial primary key as opposed to serial not null? Because in designing previous schemas, I've used serial primary key. So I'm just curious as to when it's the best practice, and is it,
It's always the best practice. I just forgot. Yeah, this should be primary key.
Okay.
Yeah. Primary key, I think, implies not null as well. So if you say primary key, you should get not null. Yeah, I think I was looking at some of the resources from the Relational Database Design module, and this one from Periscope Data. This was pretty good. I really like the rules, this 10 rules for a better SQL schema that they had here, and I think one of them was always having an integer primary key. So no matter what table you have, even if it's a join table, just always have an auto-incrementing integer primary key for that table. You can have other kinds of IDs and other kinds of indexes for a table, but it's a really good practice, and it kind of simplifies things if you just know that every table has its own ID. Any other questions, thoughts, musings? Okay. All right, folks. Well, I will post this video and the slides in Slack, and also share them on all up to the curriculum with links to them as well, so you can reference them later. Just so you know, on Wednesday, I'll be talking about, RESTful API design. And I'll be continuing with the Quora example. So these two topics kind of played nicely together. So I'll basically sort of pick up where we left off today with this concept of a Quora application or a Quora clone, and build a REST API on top of this database. So I hope to see you there for that. And if you have any other questions or want to talk about the concepts we covered in today's lecture anymore, feel free to just post a link on Slack or ping me in Slack. All right. Bye, everybody. Thanks for coming.
Thanks, Anna.